Welcome, and settle in. Tonight, we're going to explore one of nature's most captivating phenomena together, a spectacle that has mesmerized humanity since the first sparks danced across ancient skies. We're going to understand lightning, to feel the quiet wonder of electrical storms, and to discover the mysteries hidden in those brilliant flashes that cut through darkness. This is a journey into the science of lightning, told gently, told slowly, so you can drift peacefully while learning about the extraordinary forces that shape our atmosphere. If you find this soothing, if this brings you calm, consider subscribing to join us on more tranquil explorations. But for now, take a deep breath. Let your shoulders drop and allow yourself to simply be here, curious and comfortable. As we begin, lightning begins not with the flash we see, but with something far more subtle, something invisible. It begins with the whisper of particles, with the gentle separation of charges in the vast cathedral of a storm cloud. To understand this beginning, we need to step back and consider something wonderfully simple: the nature of electrical charge itself. Everything around us, every atom, every molecule in the air you're breathing right now, carries within it a delicate balance. Protons hold positive charges, electrons carry negative ones, and when everything sits in equilibrium, the world feels electrically neutral, peaceful. But introduce movement, introduce collision, introduce the chaos of a growing thunderstorm, and that balance begins to shift. Picture the atmosphere as a vast ocean of air, mostly invisible to us, mostly still on a calm day. But when conditions align, when warmth rises from sun, baked ground and meets cooler air above, something remarkable begins. Air masses start to churn, to rise and fall in great invisible currents. Water vapor, that humidity you feel on a summer afternoon, gets carried upward on these currents, lifted higher and higher into the atmosphere, where the temperature drops. Up there, miles above the ground, the water begins to change. It condenses into droplets, then freezes into tiny ice crystals, delicate as snowflakes, suspended in the turbulent air. Here is where the story gets truly fascinating. These ice particles, these frozen droplets, they don't just float serenely, they collide in the heart of a developing thunderstorm, in that zone between roughly -15 and -25 degrees Celsius. There exists a peculiar mixture. Small ice crystals dance alongside larger particles called whirlpool, which are essentially soft hail, formed when supercooled water droplets freeze onto existing ice. Supercooled water is one of nature's quiet marvels, liquid water existing below freezing temperature, because it hasn't yet found the right surface or disturbance to trigger its transformation into ice. This water clings to ice particles, building them up, creating these pull pellets that are denser, heavier than the delicate crystals floating nearby. The storm's updrafts, those powerful currents of rising air, they carry the lighter ice crystals upward, always upward, toward the top of the cloud. Meanwhile, the heavier pull either hangs suspended in the churning middle region or begins its descent, pulled by gravity. And as these particles pass each other, as the rising crystals brush against the falling or hovering pull, something extraordinary happens. They exchange charge. The exact mechanism is still being studied, still being refined by scientists. But the effect is clear and consistent. The smaller ice crystals tend to become positively charged, while the larger grow. Pull particles accumulate negative charge. You might wonder why this happens, why charge transfers during these collisions. The process involves the supercooled water, the temperature gradients within the cloud, even the microscopic structure of ice itself. When particles collide and rebound, electrons, those tiny carriers of negative charge, move from one particle to another. The specifics depend on temperature, on the presence of that supercooled water, on the relative sizes and speeds of the colliding particles. But the pattern emerges again and again, small and light, acquiring positive charge, large and heavy gathering negative charge. And so the cloud begins to organize itself electrically. The positive charges, carried by those lightweight ice crystals, accumulate at the top of the storm cloud, pushed ever higher by the relentless updrafts. This upper region can extend outward, spreading horizontally in what meteorologists call the anvil of the thunderstorm, that flat, spreading top you might have noticed when looking at distant storms. The anvil forms when rising air reaches the tropopause, that boundary layer between the troch-poch, sphere where weather happens, and the stratosphere above. The air can't rise much further, so it spreads outward instead, creating that characteristic flattened appearance. And with this spreading goes the positive charge, distributed across a vast area, sometimes extending tens of miles from the storm's core. Meanwhile, the negative charges, clinging to the pull concentrate in the middle and lower portions of the cloud. The result is a separation, a growing divide, with positive charges gathering above and negative charges amassing below. This separation happens relatively quickly once the storm reaches maturity, once the updrafts are strong enough, and the collision processes are vigorous enough. Within 15 to 20 minutes of a thunderstorm's rapid development phase, measurable electrical fields begin to establish themselves. Within half an hour, the charge separation might be sufficient for the first lightning flashes to occur. The amount of charge involved is substantial. A typical thunderstorm cloud might accumulate tens of coulombs of separated charge spread throughout its structure. To put that in perspective, a coulomb is already a significant quantity of charge. Static electricity shocks that you experience in daily life involve microcoulombs, millionths of a coulomb. The charged balloon that sticks to a wall after you rub it on your hair holds only a tiny fraction of a coulomb. But a storm cloud, with its vast volume and countless colliding particles, can separate charge on a completely different scale, building up reservoirs of positive and negative charge that would be unimaginable in everyday electrical situations. But to raise more complexity here, another layer to this electrical architecture, near the base of the cloud, where precipitation is forming, where rain might be starting to fall, a small pocket of positive charge can develop. This happens because of the precipitation itself, because of the way water droplets interact with the cloud's electric field, and because of the warmer temperatures down near the cloud's bottom. Falling rain and ice can carry charge with them, and the electrical properties of water droplets in strong fields create local charge redistributions. The result is that small but significant positive charge region at the cloud base. So we end up with a structure, a tripolar arrangement, positive at the top, negative in the middle, and a smaller positive region at the base. This three-layer structure is characteristic of mature thunderstorms, though the relative strengths and exact positions of each charge region can vary storm by storm. Now remember, this isn't happening in isolation. The cloud doesn't exist separate from the world below. The Earth and its atmosphere form a global electrical circuit, with charge constantly flowing between the ground, the atmosphere, and the ionosphere high above. Fair weather areas, regions without storms, experience a gentle downward current of positive charge from the upper atmosphere to the surface. This current is tiny, barely measurable, but continuous. Thunderstorms, meanwhile, act as the batteries in this global circuit, pumping charge back upward through lightning, maintaining the potential difference that drives the fair weather current elsewhere. Beneath this brewing storm, the ground itself responds. The Earth's surface normally carries a slight negative charge, subtle and spread thin. You walk on ground that holds more electrons than protons. Though the imbalance is so slight, you'd never notice it without sensitive instruments. But when a thunderstorm drifts overhead, when that massive concentration of negative charge builds in the cloud's middle section, everything changes. That negative charge in the cloud repels the negative charges on the ground directly beneath it. Electrons in the soil, in the trees, in the buildings, in you if you're standing outside, they flee from the cloud's influence, driven away like magnets of the same pole, repelling each other, leaving behind a concentration of positive charge on the surface. This isn't a slow process. As the storm approaches, as the cloud's charge grows stronger, the ground's response becomes more pronounced. The positive charge accumulates, mirrors the negative charge above, creating an image charge that strengthens the overall electric field between cloud and ground. It's almost as if the ground is reaching up electrically toward the cloud, responding to the electrical stress building in the atmosphere above. This positive charge isn't uniform across the landscape. It accumulates more intensely at points. At anything tall, anything that reaches upward, anything that extends closer to that negatively charged cloud base. The concentration happens because electric fields are stronger near sharp points and edges, a principle called the point discharge effect. A lightning rod on a roof, the mast of a boat, a lone tree in a field, even a person standing upright in an open area. These become islands of concentrated positive charge, responding to the electric field established by the storm above. If the field is strong enough, these pointed objects might even emit a faint glow, a phenomenon called corona discharge or St. Elmo's fire, where the concentrated electric field ionizes the air right at the tip, creating visible light. Sailors have observed St. Elmo's fire on ship masts for centuries, that eerie glow appearing during storms, sometimes accompanied by a hissing or crackling sound. It's a sign that the electric field is intense, that lightning conditions are developing, that the atmosphere is charged and stressed and approaching its breaking point. The invisible connection is forming. The stage is being set, though nothing visible has happened yet. The electric field between cloud and ground is growing with each passing moment, becoming stronger, more intense, stretching the insulating properties of air closer to their limit. If you could somehow visualize electric field lines, you'd see them bowing downward from the cloud, concentrating at the tallest objects below, creating patterns of stress in the atmosphere. Regions where the field strength is highest, where the breakdown will most likely initiate. Cosmic rays play a role here too. Another layer of wonder in this unfolding story. High-energy particles from beyond our solar system, remnants of distant stellar explosions, supernovas that occurred thousands or millions of years ago. They constantly rain down through our atmosphere. These particles, mostly protons, but also heavier nuclei, carry enormous energies, some reaching levels that we can barely achieve in our largest particle accelerators. When these cosmic particles collide with air molecules high in the atmosphere, they create cascades of secondary particles, showers of electrons, muons, photons, all spreading outward and downward from the initial impact point. Some of these secondary particles are electrically charged, and as they pass through the atmosphere, they leave trails of ionization, temporary paths where air molecules have been stripped of electrons, where the air has become momentarily more conducting. These ionization trails provide the initial seeds of conductivity in air that would otherwise be a near-perfect insulator. They create weak spots, tiny filaments of enhanced conductivity that can help initiate electrical breakdown when fields are strong enough. There is even a theory called runaway breakdown that suggests cosmic ray particles and their associated ionization cascades might be the trigger that starts the stepped leader formation. The theory proposes that energetic electrons in these cascades, accelerated by the strong electric field in the cloud, can create avalanches of additional ionization, growing exponentially, eventually forming the conducting channel that becomes the stepped leader. This connection between lightning and cosmic rays, between thunderstorms and the remnants of distant stars, is another reminder that even the most earthly phenomena have roots stretching across the universe. The same supernova that enriched our solar system's primordial gas cloud with heavy elements billions of years ago might have descendants, cosmic ray particles, playing a role in triggering lightning strikes today. As charges continue to separate within the cloud, as updrafts carry more positive charges upward and gravity pulls negative charges downward, the electric field grows stronger. The atmosphere between the cloud and ground becomes stressed. Electrically speaking, air, under normal conditions, is an excellent insulator. It doesn't conduct electricity easily. The electrons in air molecules are bound tightly to their atoms, content to stay put. But every insulator has a breaking point, a threshold beyond which it can no longer maintain its resistance. For air at sea level, this threshold is extraordinarily high, roughly 3 million volts per minute ether, a truly tremendous amount of electrical potential. Yet, thunderstorms can build even more charge than this, can create electric fields that push against this limit. The separation of charge within the cloud grows more extreme with each passing minute, each new collision between ice particles, each cycle of rising and falling air. The potential difference between the cloud and ground increases, building tension like a drawn bow, storing energy in the electric field itself. The atmosphere holds this tension, maintains it, until finally, inevitably, the threshold approaches. Something has to give. The insulating properties of air, so reliable under ordinary circumstances, begin to falter, and this is where our story shifts, where the invisible preparation gives way to the dramatic discharge, where the buildup of charge transforms into the lightning we know. The discharge begins with something called a stepped leader, though we cannot see it form. This is an invisible streamer of ionized air, a path of conducting plasma that extends downward from the cloud base in a jerky, zigzagging fashion. It's searching, in a sense, probing for the path of least resistance toward the ground. The stepped leader doesn't move smoothly, like a falling object or a flowing liquid. Instead, it advances in discrete jumps, each step extending the channel by roughly 30 to 50 meters, before pausing briefly, reorganizing, gathering charge, then lunging forward again in another step. These steps happen incredibly fast, each one taking only about a microsecond, a millionth of a second, far too quick for human eyes to register as separate events. Even if the stepped leader were bright enough to see, which it usually isn't, our eyes couldn't resolve the individual steps. They would blur together into what might appear as smooth motion. But high-speed cameras, operating at thousands or millions of frames per second can capture the stepped nature of the leader's descent. These recordings reveal the complexity of the process, show how the leader branches, how some branches die out, while others continue, how the path isn't predetermined but emerges from the local conditions the leader encounters as it descends. Each step represents a localized breakdown event, a sudden surge of ionization extending the conductive channel. As the stepped leader descends, it's carrying negative charge down from the cloud, transferring that accumulated charge along the developing pathway toward the ground. The leader channel itself is a thin tube of plasma, perhaps only a few centimeters in diameter, but highly conductive compared to the surrounding air. The current flowing in the stepped leader is relatively modest by lightning standards, perhaps 100 to 1000 amperes, but that's still substantial, far more than enough to be deadly if you could somehow touch it. How does it do this? How does a stepped leader create this conducting pathway through insulating air? By ionizing the air molecules it encounters, stripping electrons from atoms, transforming the neutral insulating air into a conducting plasma. The tip of the stepped leader is where the action happens. Here, the electric field is intensely concentrated, focused at a point, and this concentration is what allows the leader to overcome the air's resistance locally, to punch through bit by bit. Think of it like this: air can resist a certain amount of electric field before breaking down, but that resistance can be overcome if you focus enough field strength in a small enough area. The stepped leader tip does exactly this. The field at the tip exceeds the breakdown threshold for air, causes local ionization, extends the channel by one step. Then the tip pauses. The charge redistributes along the now longer channel. The field builds up again at the new tip position, and the next step occurs. Behind the leader tip, the channel it's created remains conducting, maintains its ionization, creating essentially a wire of plasma stretching back toward the cloud. This channel doesn't cool immediately. The ionization persists for milliseconds, long enough for the subsequent return stroke to use the same path. The plasma channel is hot, though not as intensely hot as it will become during the return stroke. Temperatures in the stepped leader channel might reach 10 to 20,000 degrees, hot enough to ionize, to maintain conductivity, but not yet the extreme temperatures that will develop momentarily. The path it takes appears jagged, branching, unpredictable. This zigzagging nature reflects the stepped leader's search for the easiest route down. Air isn't perfectly uniform. Pockets of moisture, dust particles, previous ionization from cosmic rays. All these create slight variations in conductivity. The stepped leader follows these variations, taking advantage of any path that offers slightly less resistance. Sometimes it branches, sending out multiple exploratory tendrils, though typically one main channel dominates. All of this happens in near darkness, invisible to observers on the ground. The stepped leader is faint, carrying relatively little current, just enough to maintain its ionization and extend the channel. But it's moving fast, descending at speeds of around 100,000 to 200,000 kilometers per second econt, roughly 1/3 to 2/3 the speed of light, though this varies between steps. From cloud to ground, depending on the height of the cloud base, this journey might take 30 to 50 milliseconds, a fraction of a second, yet an eternity on the timescale of atomic processes. Meanwhile, as the stepped leader approaches the ground, something else begins to happen. Remember that positive charge that accumulated on the surface, concentrated especially at tall objects? That charge responds to the approaching negative leader when the stepped leader gets close enough, typically within a few tens to a couple hundred meters of the ground. The electric field at the surface becomes intense enough to initiate upward streamers, positive charges reaching upward from the ground, trying to meet the descending leader. These upward streamers extend from anything elevated, anything reaching skyward. A church steeple, a metal tower, a tall tree, even the raised hand of a person foolish enough to be standing outside. All can emit these upward streamers. The streamers don't travel as far as the stepped leader. They might only extend 10, 20, perhaps 50 meters upward, but they're crucial. They're the ground's response to the approaching discharge, the positive charge stretching up to meet the negative charge coming down. And then, in a moment that transforms everything, one of these upward streamers makes contact with the tip of the stepped leader. Connection. The circuit is complete. A conducting path now exists between cloud and ground, a channel of ionized air, a plasma wire connecting negative charge in the cloud to positive charge on the surface. Think of it as completing an electrical circuit that has been building, growing more powerful with each passing minute of charge separation. The cloud is like one terminal of a battery, the ground like the other, and the stepped leader has just connected them with a wire. And the instant this connection forms, the main discharge begins. The moment we've been building toward through all this preparation. What happens next is called the return stroke. And this is what we see as lightning, the brilliant flash that illuminates the sky and sears itself into memory. The return stroke is a massive surge of electrical current, flowing both downward from the cloud and upward from the ground, meeting and mixing in the channel. But the dominant visible effect is actually upward from ground to cloud. This might seem counterintuitive since we talk about lightning striking down, since we imagine electricity flowing from cloud to ground, but the physics are subtle. The stepped leader did move downward, did create the initial path, but once connection is made, the return stroke moves upward, racing up that established path at incredible speed. The mechanism works like this. When the downward moving stepped leader tip connects with an upward moving streamer, suddenly the large reservoir of positive charge on the ground has a direct path to the negative charge in the cloud. The ground charge At the same time, negative charge from the cloud continues to flow downward, neutralizing the positive charge, completing the circuit. But the bright flash, the intense heating, the visible lightning channel we see, these are dominated by the upward, propagating wave of ionization and current. Think of it like releasing water from a dam. The stepped leader is like drilling a tunnel through the dam wall. When the tunnel breaks through, water doesn't just dribble out. It surges, it explodes through the opening, driven by all the pressure that's been building behind the dam. The return stroke is similar, an explosive release of accumulated electrical potential, charge rushing through the newly opened channel, driven by the voltage difference that's been growing between cloud and ground. The return stroke carries tremendous current, typically around 30,000 amperes for a negative lightning strike, though this can vary from a few thousand to over 200,000 amperes in particularly powerful strikes. 30,000 amperes. To put that in perspective, a household circuit breaker typically trips at 15 or 20 amperes. The electrical panel serving your entire home might be rated for 100 or 200 amperes total. A single lightning return stroke carries current equivalent to 150 to 200 houses at full electrical load, all flowing through a channel only centimeters wide. This is far more than enough to power thousands of homes, more than enough to weld metal, to vaporize any conductor not specifically designed to handle such currents. The sheer intensity of current is part of what makes lightning so dangerous and so destructive. This current flows through the narrow channel created by the stepped leader, that thin tube of plasma just a few centimeters in diameter, maybe 5 to 10 centimeters at most. The resistance of even ionized air, even highly conducting plasma, means that all this current flowing through such a small space creates enormous heat, instantaneous and extreme. It's the same principle as an incandescent light bulb. Current flowing through a thin wire causes heating, but amplified beyond any domestic electrical experience. The temperature in the lightning channel spikes to around 50,000 degrees Fahrenheit, roughly 30,000 degrees Celsius, or approximately 30,000 Kelvin in scientific units. This is 5 times hotter than the surface of the sun, 5 times the temperature at the visible surface of our star. To put this in perspective, the sun's surface, that layer we see when we look at it through protective filters, sits at about 6,000 degrees Celsius. The core of the sun is far hotter, tens of millions of degrees where nuclear fusion occurs. But the surface, the photosphere, is about 6,000 degrees. Lightning achieves 5 times that temperature, at least briefly, in a channel exposed to Earth's atmosphere. The air in the channel doesn't just heat up gradually. There is no time for gradual heating. The temperature rise happens in microseconds, faster than air can move, faster than pressure waves can propagate away. The air superheats. In this plasma state, atoms are ionized, electrons are free, moving separately from their parent nuclei, and the material glows brilliantly as electrons recombine and energy is released as light. This incredible temperature is what makes the channel glow so brightly. Incandescent, radiating light across the visible spectrum and beyond, into the ultraviolet and even, briefly, into X-rays. The light is intense enough to temporarily blind someone looking directly at a close lightning strike, bright enough to illuminate landscapes for miles around, to read by even at considerable distance. The spectrum is rich, containing emissions from many elements, nitrogen from the air being the dominant source, but also oxygen and other atmospheric constituents, even sometimes elements from whatever the lightning strikes, vaporized and excited, contributing their own spectral signatures to light. The return stroke moves fast, racing up the channel at about 1/3 the speed of light, roughly 100,000 kilometers per second, econd. That's fast enough to circle the Earth about 2.5 times in a single second. Fast enough that the entire journey from ground to cloud top takes only 50 to 100 microseconds, less than 1/10 of a millisecond. During this brief moment, briefer than the blink of an eye, briefer than any conscious thought, the channel fully illuminates, becomes visible, creates the brilliant flash we associate with lightning. This is what we see. This upward, moving surge of current and light, though our eyes can't separate the direction, can't distinguish the return stroke's upward movement from our mental image and expectation of downward striking. To our perception, lightning appears instantaneous, a sudden flash that seems to happen all at once. But often, the story doesn't end with a single flash. If enough charge remains in the cloud after the first discharge, if the initial return stroke didn't fully neutralize the charge separation that had built up, additional strokes can follow down the same channel. The first return stroke might transfer 10 to 20 coulombs of charge from cloud to ground, but the cloud might have accumulated 50 or 80 coulombs total. To raise more charge available, more potential energy stored, and the conducting channel already exists, already provides an easy path for additional discharge. These subsequent strokes, called dart leaders, travel down the channel established by the first strike. They move faster than the original stepped leader because the path is already there, already ionized, already easier to traverse. A dart leader doesn't have to create a new channel through virgin air, breaking down the insulation step by step. Instead, it follows the existing path, re-ionizing the channel that has begun to cool, refreshing the conductivity, preparing for another return stroke. Dart leaders typically move at about 10 to 20,000 kilometers per second econd, still an enormous speed, about 1/10 the speed of light, but slower than return strokes and considerably faster than the original stepped leader. Each dart leader is followed by another return stroke, another surge of current from ground to cloud, another flash of light, another transfer of charge. These subsequent return strokes might carry similar currents to the first stroke, or they might be weaker or occasionally stronger, depending on how much charge is available and how the cloud's electrical structure has rearranged after the previous discharges. Typically, subsequent strokes are somewhat weaker than the first, but not always. Sometimes a later stroke can be more intense if it taps into a fresh reservoir of charge, or if the channel path has improved. A typical lightning bolt, what we perceive as a single flash, actually contains 3 to 5 of these component strokes. These dart leader and return stroke sequences occurring in rapid succession. Sometimes only 1 or 2 strokes occur, particularly in weaker lightning or in storms that are dissipating. Sometimes many more occur, up to 20 or even 30 strokes in exceptional cases have been documented. Each following the same channel, each adding to the total charge transferred and energy released. The record for most strokes in a single flash is somewhere around 25 or 30, though counting them precisely requires specialized high-speed instruments. These multiple strokes happen quickly, separated by only 40 to 50 milliseconds. Typically, sometimes less, sometimes a bit more. 40 milliseconds is 1/25th of a second, faster than our eye's persistence of vision can resolve. Human vision integrates images over about 30 to 50 milliseconds, which means individual strokes separated by 40 milliseconds blur together in our perception. We don't see them as separate events. This is why lightning often appears to flicker, to pulse. We're not seeing one smooth flash, but several distinct strokes occurring in rapid succession, each following the same channel, each reinforcing the appearance of a single jagged bolt flickering in and out of existence. The whole sequence, from first step leader to final return stroke, might last 200 to 500 milliseconds total, about half a second, though most of the visible flashing is concentrated in shorter bursts. Each stroke might carry similar or different amounts of current, transferring varying amounts of charge, might be slightly brighter or dimmer, depending on the specific conditions for that stroke. The first stroke often appears brightest, being the initial discharge and often carrying the most current. Subsequent strokes tend to be fainter, though not always noticeably so. The cumulative effect of multiple strokes is that a single lightning flash, what we think of as one bolt, might transfer 40 to 50 coulomb of charge total, releasing energy equivalent to a few 100 million joules. Roughly the energy in 100 kilograms of TNT exploding over a longer time period and in a different form. Now, what I've described so far is negative lightning. The most common type, accounting for about 90 to 95% of all cloud to ground strikes. It's called negative because negative charge from the cloud is being lowered to the ground, even though the visible return stroke moves upward. But there exists another variety, less common but more powerful, called positive lightning. Positive lightning originates from the positively charged upper regions of the thunderstorm, that anvil section where the updrafts carried all those lightweight, positively charged ice crystals. These strikes are rarer, making up perhaps 5 to 10% of cloud to ground lightning, but they're notable for their intensity. Positive lightning typically carries much higher peak currents, sometimes exceeding 100,000 amperes, and can transfer enormous amounts of charge, up to several hundred coulombs, compared to the 15 or 20 coulombs typical of negative strikes. Positive lightning often travels greater distances from the storm before striking the ground. These are the bolts from the blue lightning that seems to come from clear sky because it originates from the distant anvil, far from the main precipitation area, and strikes ground miles away from where rain is falling. A positive lightning bolt can travel 10 miles or more horizontally before turning downward to strike. You could be standing in sunshine, thinking the storm is far away, and still be struck by positive lightning extending from that distant anvil. The power of positive lightning comes from the larger reservoir of charge. It can access the entire upper region of a mature thunderstorm, holds vast amounts of positive charge, spread over a wide area. When positive lightning initiates, it can draw on this extensive supply, sustaining higher currents for longer durations than negative strikes. The resulting flash is often singular, bright, and intense. Without the multiple strokes typical of negative lightning, it's a single, powerful discharge, rather than a flickering series. But not all lightning travels between cloud and ground. In fact, the majority doesn't. Cloud to cloud and intra-cloud lightning, discharges that occur entirely within or between clouds, account for roughly 75 to 80% of all lightning activity. These discharges follow similar physical processes: the buildup and separation of charge, the formation of leaders, the surge of current, but they connect different charged regions without ever reaching the ground. Intra-cloud lightning is the most common variety of all. It occurs within a single cloud, typically connecting the negative charge region in the middle of the storm to the positive charge region at the top. Because these discharges happen inside the cloud, we often can't see the channel directly. Instead, we see the cloud itself light up, glowing from within, as the lightning channel illuminates the water droplets and ice crystals. This is sometimes called sheet lightning, though that term more properly refers to any lightning too far away for us to distinguish individual bolts, where we see only the generalized glow. Cloud to cloud lightning travels between separate storm cells or separate clouds, connecting charged regions across open air. These can create spectacular displays, with visible channels stretching horizontally across the sky, connecting one storm to another. Sometimes these channels cover enormous distances, 10 or 20 miles, sustained by the vast charge differences between separate storm systems. The preference for in-cloud and cloud to cloud lightning makes sense when you consider the electric fields involved. The distance between the negative and positive charge regions within a cloud is much smaller than the distance from cloud to ground. The electric field strength, which depends on both the amount of charge and the distance separating opposite charges, can more easily exceed the breakdown threshold for air along the shorter paths inside or between clouds. It's simply easier, electrically speaking, for lightning to discharge within the cloud structure than to bridge the larger gap to ground. This doesn't make cloud to ground lightning rare, of course. Millions of ground strikes occur worldwide every day, but it means that for every bolt we see striking Earth, several more are flickering through the clouds themselves, redistributing charge, maintaining the storm's electrical balance, continuing the constant process of breakdown and discharge that characterizes active thunderstorms. Understanding all of this, the charge separation, the leader formation, the return stroke, the varieties of lightning paths, we begin to appreciate the complexity hidden in what appears to be a simple flash. Each lightning bolt represents the culmination of countless molecular collisions, precise electrical processes, atmospheric dynamics, operating on scales from the microscopic ice crystal to the miles-high storm system. The flash we see, brilliant and brief, is the final act of an elaborate sequence, the visible signature of invisible forces that have been building for minutes or hours. And there is something profound in recognizing this, in understanding that the lightning illuminating a summer storm isn't random, isn't chaotic in the sense of being without order, but rather follows deep physical principles, responds to fundamental laws that govern all electrical phenomena, the same principles that make your static shock after shuffling across carpet, the same forces that power your devices, the same electromagnetic interactions that structure matter itself. These are at play in lightning, just amplified, just unleashed on a scale that can light up the night and trees and fuse sand into glass. The flash comes first, instant and silent across the distance, light reaching our eyes at its incredible speed of 300 million meters per second econd, essentially instantaneous over the kilometers that separate us from storms. But then, after a pause, after a delay that depends precisely on distance, the sound arrives. Thunder, that deep rumble, that sharp crack, that rolling boom that seems to travel across the landscape, moving through hills and valleys, echoing off buildings and trees, sometimes lasting for many seconds, sometimes arriving as a single sharp report. Thunder is lightning's acoustic signature, its announcement in sound of what we've already witnessed in light, its way of reaching us through a different sense, a different channel. And like everything about lightning, thunder emerges from fascinating physics, from processes that transform electrical energy first into extreme heat, then into one of nature's most powerful sounds. Let me take you back to that lightning channel, that narrow column of superheated air glowing at 50,000 degrees, that filament of plasma hanging in the atmosphere for those brief microseconds of the return stroke. When the return stroke surges through this channel, heating it so intensely in just a few microseconds, faster than the time it takes sound to travel a single meter, the air responds in the only way it can. It expands. But this isn't gentle expansion, like inflating a balloon slowly. Isn't the smooth thermal expansion you feel from a radiator warming a room. This is explosive, violent, faster than sound itself can normally travel through air. The air in and immediately around the lightning channel, heated from ambient temperature to plasma temperatures in less time than a heartbeat's fragment, expands outward at supersonic speeds, compressing the cooler air in front of it with tremendous force. When something moves through air faster than sound travels in that air, it creates what's called a shock wave, a discontinuity in pressure that propagates outward as a wavefront. You might be familiar with this concept from supersonic aircraft, jets that break the sound barrier and generate that distinctive sonic boom, that sharp report that rattles windows and startles people below. The shock wave from a supersonic aircraft is formed by the accumulation of pressure waves that can't propagate away from the aircraft fast enough, building up into a cone of compressed air trailing behind. Lightning creates a similar phenomenon, but the mechanism and geometry are different. Instead of a physical object moving through air, we have air itself expanding so rapidly that it compresses neighboring air faster than pressure waves can propagate away. The result is a cylindrical shock wave, expanding outward from the lightning channel in all radial directions. Perpendicular to the channel's length, a tube of compressed air radiating outward at supersonic speed. This initial shock wave is intensely powerful, carrying enormous acoustic energy. Close to the lightning channel, within just a few meters, the pressure can spike dramatically, reaching several times normal atmospheric pressure, creating an overpressure pulse that can damage structures, break windows, harm human tissue if you're close enough. The air is compressed violently, then rarefied as the wave passes, creating both positive and negative pressure excursions. If you've ever been very close to a lightning strike, within a few hundred meters, close enough to feel truly frightened by the immediacy of it, you might have felt this pressure wave physically, a compression that you sense as much as hear, a thump in your chest, a pressure change in your ears, your whole body registering the acoustic assault. But shock waves don't maintain supersonic speeds indefinitely. As they propagate outward, as they travel away from their source, they lose energy to the air around them through friction, through the process of compressing and moving air molecules, through the gradual spreading of energy over an ever larger wavefront. The shock wave weakens with distance, its peak pressure decreasing, its speed reducing. Within about 10 meters from the lightning channel, typically even closer for weaker strokes, the shock wave has decelerated enough to become a regular sound wave, traveling at the normal speed of sound for the ambient air conditions, roughly 340 meters per second econd at sea level in typical temperatures, though this varies with temperature and humidity. This transition from shock wave to sound wave is gradual, not an abrupt change, but a smooth slowdown as the wave loses its supersonic character. The physics transition from shock wave dynamics, where nonlinear effects dominate and the wave itself travels faster than sound, to acoustic wave dynamics, where linear wave equations apply, and the wave propagates at the characteristic sound speed for the medium. But the effect is significant. What begins as a supersonic blast, a shock wave that could literally knock you down if you were close enough, becomes an acoustic wave, pressure oscillations moving through the air at standard sound speed, eventually reaching listeners kilometers away as the rolling thunder we know. The temperature of the air affects how fast sound travels. Warmer air molecules move faster, carry sound more quickly, so sound speed increases with temperature. On a hot summer day when thunderstorms are common, sound might travel around 350 meters per second econd, while on a cool autumn evening, it might move at only 330 meters per second econd. This variation is usually small enough that we can use a simple approximation for estimating distance. Light travels so much faster than sound, essentially instantaneous over the distances we experience weather, that we see lightning essentially at the moment it occurs. Sound, meanwhile, takes about 3 seconds to travel 1 kilometer, or roughly 5 seconds to travel 1 mile. This time difference gives us that useful rule you might have heard, the method for estimating how far away lightning struck. Count the seconds between seeing the flash and hearing the thunder. Then divide by 5 to get the distance in miles, or divide by 3 for kilometers. 10 seconds means the lightning was about 2 miles away. 3 seconds means less than a kilometer, close enough to be concerning. This method isn't perfectly accurate. Sound doesn't always travel in straight lines, but it gives you a reasonable sense of the storm's distance. But why does thunder sound different depending on where we are, how far away the lightning struck? Why do nearby strikes produce sharp, cracking sounds while distant lightning rumbles long and low? The answer lies in the geometry of the lightning channel and the way sound propagates through the atmosphere. A lightning bolt isn't a simple point source of sound. It's an extended line, often several kilometers long, stretching from cloud to ground or across portions of the cloud interior. Every point along this channel generates sound waves when it's heated by the return stroke. These sound waves emanate from different locations, different heights, different distances from any observer. The sound from the portion of the channel nearest you arrives first. The sound from portions farther away, higher in the channel, or farther along its horizontal extent, arrives later. Your ears receive a continuous stream of sound arriving from different parts of the lightning channel, spread out over time for a nearby strike, particularly if the lightning is fairly vertical and you happen to be positioned perpendicular to the bolt. You might hear what's described as a sharp crack or a loud clap. This happens when much of the lightning channel is roughly equidistant from you, so the sound from different parts arrives nearly simultaneously, or at least within a short enough time that your ears perceive it as a single, sharp impulse. The sound is intense because it's concentrated, many sources contributing at once, and it's high frequency because the rapid onset contains all the acoustic energy from the initial expansion. Move farther from the strike, and the sound changes character. Now, different parts of the channel are at substantially different distances from you. Sound from the nearest part arrives first. Then sound from successively farther portions rolls in afterward. Instead of a sharp crack, you hear a rumble, a prolonged sound that seems to roll on for seconds, sometimes building and fading in waves. This is the acoustic signature of an extended source being heard from a distance, each part of the lightning channel contributing its sound at a different time. The shape of the lightning channel matters too. Lightning isn't straight. It's jagged, branching, twisting in 3 dimensions. Researchers who study thunder acoustics talk about different levels of tor, cho, a, si, t, different scales of zigzag and curve in the lightning path. There are macro-scale bends, major turns in the channel that span hundreds of meters. There are meso-scale variations, medium-sized zigs and zags, and there are micro-scale details, small irregularities in the path. Each level of structure influences the acoustic signature. A particularly interesting effect occurs with those macro-scale bends. When a lightning channel has a major horizontal section, a significant bend running perpendicular to your line of sight, the sound from that section can arrive in a concentrated burst. This creates a secondary peak in the thunder, another clap or loud pulse superimposed on the overall rumble. Complex lightning channels, those with extensive branching and bending, produce complex thunder signatures, multiple peaks, variations in intensity and pitch, as sound from different geometric features reaches your ears. Pitch. The frequency content of thunder varies with distance too. Close thunder contains high frequencies, sharp, crisp sounds that can almost crack like a whip. These high frequencies come from the rapid onset of the expansion, from the sharpness of the initial shock wave. But high-frequency sounds don't travel well through the atmosphere. Air molecules absorb high-frequency acoustic energy more efficiently than low frequencies, a process called atmospheric attenuation. The farther sound travels, the more the high frequencies are filtered out, leaving primarily the low rumbles. Distant thunder then sounds deep and rolling because only the low-frequency components survive the journey to your ears. The sharp cracks have been absorbed, damped by their passage through miles of air. What remains is the bass rumble, frequencies below a few hundred hertz, sounds that can carry for miles. This is why very distant storms produce only low, drawn-out rumbles. Why you might hear thunder from a storm beyond the horizon without ever seeing its lightning. Terrain plays a role in shaping what you hear. Buildings, hills, forests, all these can reflect sound waves, creating echoes that add to the complexity of thunder. In a city, thunder might bounce off tall buildings, arriving at your ears from multiple directions, reinforcing and interfering with itself. In mountainous terrain, echoes from valley walls can extend the duration of thunder, making it seem to roll through the landscape for many seconds. Over flat, open areas with few obstacles, thunder tends to be more straightforward, less complicated by reflections, though you still get that extended rumble from the geometry of the lightning channel itself. There is also a phenomenon involving temperature that can dramatically affect how thunder sounds and how far it travels. Normally, air temperature decreases as you go higher in the atmosphere. Sound waves traveling through this typical temperature profile tend to bend upward, refracting away from the ground because they travel faster in the warmer air near the surface than in the cooler air above. This upward refraction means that thunder beyond a certain distance, typically around 10 to 15 miles in normal conditions, might refract entirely over your head, never reaching your ears even though the lightning was bright enough to see. But sometimes atmospheric conditions create what's called a temperature inversion. This occurs when a layer of warm air sits above cooler air near the ground, reversing the normal temperature gradient. Temperature inversions are common during winter, when thunderstorms develop in warm air masses moving over cold ground. They can also occur in the early morning after a cold night, or in valleys where cold air has drained downward and pooled. When sound waves from thunder travel through an inversion, they bend downward instead of upward. The sound refracts toward the ground because it moves slower in the cool surface air than in the warm air above. This downward bending can dramatically enhance how far and how loudly thunder travels. Sound that would normally refract away into the upper atmosphere instead curves back down, reaching listeners much farther from the strike. Thunder during inversions can be startlingly loud even from relatively distant lightning, and it can travel much farther, sometimes audible from 20 or 25 miles away instead of the usual 10 or 15. The experience of being close to lightning, truly close, within a few hundred meters, is visceral and unforgettable. The sound isn't just loud, it's felt, a physical impact that you experience through your whole body, not just your ears. This is partly the intensity of the acoustic energy. Thunder at close range can exceed 170 decibels, far above the threshold of pain for human hearing. But it's also those residual properties of the shock wave, pressure changes that affect your entire body, compression waves that you sense through multiple channels. People who've been near lightning strikes describe the sound as a sharp, ripping crack followed immediately by an overwhelming boom, sometimes accompanied by a fizzing or tearing sound. The crack is the high-frequency content, the sharp onset from the nearest part of the channel. The boom is the main acoustic pulse, the bulk of the energy. And that fizzing or tearing quality might be the sound of the stepped leader, of branches, of the complex fine structure of the discharge, happening faster than the main boom can resolve. Beyond the audible thunder, there is also infrasonic thunder, sound waves with frequencies below 20 Hz, below the range of human hearing. These low-frequency waves are generated by the lightning discharge, particularly by the large-scale processes in cloud discharges, where significant volumes of air are suddenly displaced. Infrasonic thunder can travel extremely far, hundreds or even thousands of kilometers, because low-frequency sound is barely attenuated by the atmosphere. Researchers use specialized instruments to detect and study infrasonic thunder, learning about distant lightning activity that would otherwise be undetectable. Some scientists have even captured images of thunder, using arrays of sensitive microphones to map the acoustic sources along a lightning channel. By precisely timing when sound arrives at multiple microphones and using sophisticated signal processing, they can reconstruct where the sound came from, effectively creating an acoustic picture of the lightning bolt. This technique has revealed details about how different parts of the lightning channel emit sound, how return strokes and stepped leaders each contribute their acoustic signatures, helping to refine our understanding of the discharge process itself. Thunder, then, is more than just noise. It's information, a detailed acoustic record of the lightning that produced it, encoding the channel's length, shape, orientation, the power of the discharge, the atmospheric conditions through which the sound traveled. Every rumble and crack tells a story if you know how to read it, reveals something about the electrical storm playing out above. Now let's explore the remarkable variety that lightning can display, the different forms and phenomena that make each storm unique, each flash distinct. While the basic physics remains consistent, charge separation, leader formation, return stroke, the details of how lightning appears can vary dramatically depending on conditions, on the storm's structure, on the observer's perspective, on chance and chaos in the atmospheric dance. We've already mentioned the most common appearance, that jagged, branching bolt that we typically picture when someone says lightning. This is forked lightning, named for the way it splits and branches as it descends or travels through the cloud. The branching happens because the stepped leader sometimes sends out multiple exploratory paths, or because the electric field isn't uniform, allowing multiple routes to develop simultaneously. The result is that characteristic tree-like pattern, a main trunk with numerous branches spreading outward, each branch a potential path for the discharge. But not all lightning looks like this. Ribbon lightning creates a striking visual effect, where what appears to be a single bolt becomes multiple parallel streaks, like a ribbon with several folds. This occurs when strong crosswinds blow across the lightning channel during a multi-stroke flash. Remember, a typical lightning bolt contains multiple return strokes following the same channel, each stroke separated by 40 or 50 milliseconds. If wind is moving the air where the lightning forms, each successive stroke gets displaced slightly to the side of the previous one. Your eye, seeing all these strokes within a short time, perceives them as parallel bands, a ribboning effect. The faster the wind, the more separated the ribbons appear. Bead lightning presents a different mystery, one that appears in the decay phase after a lightning channel has discharged. As the channel cools and the ionization begins to fade, sometimes it breaks up into a series of bright spots or beads, like pearls on a string, persisting for just a fraction of a second longer than the continuous channel. The beads might represent portions of the channel that had particularly intense currents, or regions where the ionization decays more slowly due to local conditions. Some researchers think bead lightning is simply a normal lightning channel seen at a particular moment in its cool down. The beating visible whenever we happen to be looking during that brief transitional phase. Sheet lightning is less a different type of lightning and more a matter of perspective. When you see a storm from a distance, particularly at night, and you observe flashes that illuminate entire sections of cloud without seeing distinct bolts, that's sheet lightning. What you're seeing is lightning occurring within or behind the cloud, the channel itself hidden from your view, but its light scattered and reflected by water droplets and ice crystals. The cloud acts as a diffuser, turning the point source of the lightning channel into an area source, the whole cloud base or side glowing briefly with each discharge. All intra-cloud and many-cloud to cloud lightning events appear this way from ground level. Heat lightning is similar, a term for lightning flashes seen on a distant horizon, usually on warm summer evenings, with no accompanying thunder. The name is somewhat misleading because it suggests the lightning is caused by heat. But it's just ordinary lightning from thunderstorms too far away for their thunder to reach you. You see the flashes, perhaps illuminating distant clouds or reflecting off the sky itself, but the storm is 20 or 30 or 40 miles away, well beyond the range where thunder remains audible. The atmosphere between you and the storm might be perfectly clear, the air still and warm, hence the association with heat, but the lightning itself is the same cloud. To ground and intra-cloud discharges happening in any thunderstorm. Then to raise the enigma, the phenomenon that has puzzled scientists and sparked debate for centuries, the mysterious appearance that walks the line between verified reality and persistent mystery. Ball lightning. Reports of ball lightning go back hundreds of years, centuries of descriptions from credible observers, sailors and scientists, pilots and professors, farmers and philosophers, all describing the same basic phenomenon: luminous spheres, glowing balls of light that float through the air, pass through windows, roll along the ground, hover in rooms, descend chimneys, drift down airplane aisles, behave in ways that seem to defy our understanding of plasma physics and electrical discharges, sometimes exploding with a bang, sometimes fading quietly away, sometimes simply disappearing as mysteriously as they appeared. The descriptions are remarkably consistent across time and culture, across continents and centuries. The balls are typically orange, yellow, or bluish, white in color, though red, green, and other hues have been reported. They glow steadily or pulse, emit light bright enough to see by, but rarely so bright as to be blinding. They're usually described as roughly the size of a grapefruit or basketball, somewhere between 10 and 30 centimeters in diameter, though reports range from objects as small as a few centimeters, pea-sized luminous spheres, to massive balls several meters across, though these extreme sizes are rare. The smaller sizes seem most common, with most credible reports describing balls somewhere between 10 and 50 centimeters across. They last longer than any normal lightning, typically 5 to 10 seconds from appearance to disappearance, sometimes as long as a minute, or even more in extraordinary accounts. Though these longer durations are less well verified, this duration alone is puzzling. Normal lightning. The return stroke channel lasts microseconds to milliseconds, the longest lasting lightning phenomena we understand, like continuing currents in positive lightning, might persist for a few hundred milliseconds. but ball lightning reportedly lasts seconds, orders of magnitude longer than any conventional electrical discharge, should persist without a continuous energy source. They often move slowly, drifting horizontally, seeming independent of wind, though sometimes they move with apparent purpose, following walls or metal objects like power lines or fences. This motion is usually described as slow, walking pace or slower, floating rather than flying. Sometimes, ball lightning appears stationary, hovering in place. Sometimes it bounces, touching the ground or a surface and rebounding like a rubber ball. This bouncing behavior is particularly strange, implying some kind of elastic property, some physical structure that can compress and rebound. Many reports mention a hissing, humming, or buzzing sound accompanying the ball, a continuous noise that suggests ongoing electrical or chemical activity. This sound is often compared to the sound of frying or the buzz of high-voltage equipment, and frequently, observers note a distinct smell, usually described as sulfurous, like rotten eggs or burnt matches, or like ozone, that sharp, clean smell that accompanies electrical sparks and is familiar from photocopiers or after thunderstorms. These olfactory clues suggest chemical reactions, oxidation processes, the presence of various atmospheric compounds being broken down or recombined. For a long time, centuries really, scientists were skeptical of ball lightning, dismissing reports as optical illusions. After images from regular lightning strikes producing temporary spots in observers' vision, hallucinations brought on by the stress and excitement of severe weather, or misidentifications of other phenomena like corona discharge or bioluminescent phenomena. After all, ball lightning was rarely photographed, never captured in controlled circumstances, difficult to reconcile with what we understood about plasma physics and electrical discharges. How could a ball of ionized gas, of plasma, persist for seconds without a continuous power source? Plasma disperses quickly in normal air pressure, needs continuous energy input to maintain ionization. What could power a free-floating ball of lightning? What could contain it? Keep it from simply dissipating or floating upward like a hot air balloon? The skepticism was understandable given the lack of physical evidence, but the reports kept coming. From too many credible sources, described too consistently, to dismiss entirely. Pilots reported ball lightning passing through aircraft during storms. Laboratory workers at high-voltage facilities occasionally reported ball-like glowing objects after arcing events. Ship's crews described luminous spheres during electrical storms at sea. The anecdotal evidence was overwhelming, even if hard physical data remained elusive. The turning point came in recent decades with the advent of better video recording equipment being more widely distributed. In 2012, researchers in China conducting a lightning observation campaign with high-speed video cameras accidentally captured ball lightning on video for the first time under scientific observation. They were recording normal lightning strikes for study when a ball lightning event occurred directly in their camera's field of view. Right place, right time, pure chance, but thoroughly documented. The video showed a luminous sphere moving horizontally above the ground for several seconds before dissipating. More importantly, in 2014, scientists published a spectral analysis of what appeared to be ball lightning using spectroscopic instruments that had been set up to study normal lightning but happened to catch ball lightning instead. This analysis showed that the light emitted by the ball contained emission lines from silicon, iron, and calcium, elements commonly found in soil but not typically present in air. This spectroscopic evidence was a breakthrough, providing hard physical data about composition. The first time ball lightning had been chemically analyzed. According to this theory, when normal lightning strikes the ground, particularly soil rich in silicon compounds, it can vaporize minerals. The intense heat and electrical current might create a mix of vaporized silicon and other elements. These materials, suddenly ionized and energized, could form a glowing ball of plasma, with the metal vapors providing a kind of chemical fuel. The ball glows as the silicon oxidizes, combining with oxygen in the air, releasing energy as light. The various elements present would create the different colors reported. The oxidation would produce the characteristic smell, and the chemical nature of the process could explain the relatively long lifetime compared to a pure electrical plasma. Other theories propose different mechanisms. Some suggest ball lightning might be a vortex of air, a spinning ring of atmosphere that's somehow been ionized. Others propose it's a form of microwave radiation, electromagnetic energy trapped in a bubble or shell of plasma. There are theories involving antimatter, quantum effects, exotic states of matter, but most of these lack convincing evidence or violate known physics. The silicon vaporization theory remains the most consistent with observations and plausible within established science. Yet ball lightning remains rare and unpredictable. Even the observers who captured it on video and recorded its spectrum admit it was pure luck, being in the right place with the right equipment when this fleeting phenomenon appeared. Most people will never see ball lightning in their lifetime. Those who do often describe it as dreamlike, surreal, a moment when the ordinary rules seemed suspended, and something strange and beautiful manifested briefly before vanishing. Positive lightning, which we touched on earlier, deserves more attention for its distinctive character and the particular hazards it presents to anyone caught outdoors during storms. While rarer than negative lightning, accounting for only about 5 to 10% of cloud to ground strikes, it's often more powerful and potentially more dangerous in every measurable way. Positive strikes typically produce a single intense flash, rather than the multiple strokes common in negative lightning. The entire discharge might consist of one powerful stroke, transferring enormous charge in a single pulse, rather than distributing it across multiple return strokes. The bolt often appears brighter, the channel wider when captured photographically, and the flash can have a distinctive bluish-white quality that some observers can distinguish from the more typical yellow, white or orange, white of negative strikes, though this color difference is subtle and not always apparent. Because positive lightning originates from the anvil of the storm, from that spreading upper region of positive charge that can extend tens of miles from the storm's precipitation core, it can strike when you least expect it, hitting areas where no rain is falling, where the sky overhead might even be partly clear, where you might think you're safe from the storms. Electrical fury. You could be standing in sunshine, watching a storm on the horizon, feeling confident because the rain and dark clouds are miles away, and still be struck by positive lightning extending from that distant anvil overhead. This is the origin of the phrase, bolt from the blue. Lightning that strikes from apparently clear sky, from regions where the threat isn't obvious. The danger is compounded by the fact that positive lightning strikes can travel horizontally for 10, 15, even 25 miles before turning downward to strike the ground. Most of this horizontal travel occurs in the clear air of the anvil region or beyond, invisible, giving no warning, no obvious connection to the storm that spawned it. The visible portion, the vertical strike to ground, might be the only part you see, appearing to come from nowhere, if the storm's main body is beyond the horizon or obscured by terrain or buildings. To raise a particular hazard with positive lightning that meteorologists and safety experts emphasize repeatedly. The single, powerful discharge deposits enormous energy in a very short time, sometimes transferring charge exceeding 300 coulombs, 5 or 10 times what a typical negative strike carries. Peak currents can exceed 100,000 amperes, 2 or 3 times the typical negative lightning current. This concentration of energy and current makes positive lightning more likely to cause severe damage to anything struck, more capable of starting fires, of exploding trees, of shattering concrete, of seriously injuring or killing anyone unfortunate enough to be in the path. The high charge transfer means that ground currents, electricity spreading through soil from the strike point, can be dangerous at greater distances. Someone standing 50 or 100 meters from a positive lightning strike point might still receive a dangerous or fatal shock through ground current, where negative lightning ground currents typically become non-lethal at shorter distances. Anvil crawlers represent another fascinating variant, sometimes called spider lightning for the web. Like patterns they create, these are lightning discharges that spread horizontally across the underside of the storm's anvil, typically starting as an intra-cloud flash and then extending outward, crawling across the cloud base in branching, spreading patterns. From below, anvil crawlers can be spectacular, illuminating vast areas of cloud with bright, spreading networks of light. They often occur in the later stages of thunderstorms, as the storm structure evolves and charge regions shift. Upward lightning, though less commonly observed, occurs when lightning initiates from the ground and travels upward toward the cloud, the reverse of the typical cloud to ground strike. This type usually originates from very tall structures, towers, skyscrapers, mountaintops, particularly during winter storms, or in conditions where the electric field is strong, but not quite strong enough to initiate normal downward strikes. The tall structure effectively extends the ground upward, concentrating the electric field at its top until it's sufficient to launch an upward leader. These upward strikes are important for lightning protection of tall structures and are continuously studied to improve safety systems. Each of these varieties, each form and phenomenon, reflects the complexity and variability inherent in atmospheric electricity. No two storms are quite the same. No two lightning flashes follow identical paths or display identical characteristics. The conditions that create one type of discharge might be slightly different minutes later, producing a different appearance, a different acoustic signature, a different experience for anyone watching the storm unfold. But lightning's story doesn't end at the visible spectrum, doesn't conclude with what we can see from ground level, high above the storm, in the thin air where atmosphere begins to blur into space. Another class of phenomena unfolds, transient and ethereal, discovered only recently in humanity's long relationship with thunderstorms. These are the upper atmospheric lightning events, manifestations of electricity reaching up toward space, creating displays that would seem fantastical if we didn't have photographs to prove their reality. The story begins, in a way, with prediction. In 1925, a Scottish physicist named Charles Thomson Rees-Wilson, who would later win a Nobel Prize for inventing the cloud chamber, proposed on theoretical grounds that electrical breakdown should occur high above thunderstorms. Wilson understood the physics of electric fields and atmospheric pressure. He recognized that as altitude increases, air density decreases, making it easier for electrical discharges to occur even at lower field strengths. If thunderstorms generated strong enough electric fields at their tops, Wilson reasoned, those fields might cause discharges in the upper atmosphere, creating electrical phenomena at altitudes far above the clouds themselves. But Wilson's prediction went largely unnoticed or unconfirmed for decades. Pilots occasionally reported seeing strange flashes or glows above storms, brief lights that didn't seem like normal lightning. But these observations were anecdotal, often dismissed. Without photographs, without data, the scientific community remained skeptical. The prevailing assumption was that lightning stayed within and below clouds, that nothing significant happened electrically in the upper reaches of the atmosphere. That assumption shattered on July 6, 1989, when scientists from the University of Minnesota, testing a low-light video camera for an unrelated purpose, accidentally captured something extraordinary. Above a distant thunderstorm, they recorded brief flashes of reddish light, structures that seemed to extend upward from the storm top into the clear air above. The structures were fleeting, lasting only milliseconds, but they were there, unmistakable, completely unexpected. Lightning, or something like it, was indeed occurring high above the storms. The researchers named these phenomena sprites, after the mischievous spirits of folklore, creatures like Shakespeare's Puck or Ariel, quick and elusive, dwelling in the air. The name captured both the fleeting nature of these events and the sense of wonder they inspired, a touch of whimsy in scientific nomenclature. Later, someone crafted a backronym: stratospheric and mesospheric perturbations resulting from intense thunderstorm electrification. But Sprite itself, simple and evocative, is what stuck. Sprites appear at altitudes between 50 and 90 kilometers above the Earth's surface, well above the weather. Up in the mesosphere, where the air is thin and cold, they're triggered by particularly powerful positive lightning strikes. Those intense discharges from the storms anvil to the ground. The lightning strike creates a strong electromagnetic pulse, and this pulse, propagating upward through the atmosphere, generates electric fields in the mesosphere sufficient to cause electrical breakdown, despite the already thin air. The visual appearance of sprites is striking and varied. The most common form looks somewhat like a jellyfish, with a bright central region and tendrils hanging downward, sometimes extending down to altitudes of 40 kilometers or so. These tendrils are often multiple, giving a branching, root-like appearance. The color is predominantly red, particularly in the upper portions, coming from excited nitrogen molecules in the low-pressure environment. The lower portions, those hanging tendrils, often show blue coloration, also from nitrogen, but in a different excitation state. Another common form is the column sprite, sometimes called sea sprite, which appears as a vertical column of red light, more uniform, less structured than the jellyfish type. When these columns have prominent tendrils, they're sometimes nicknamed carrot sprites for their resemblance to that vegetable. Wider at the top and tapering to thin tendrils below. Sprites can occur individually, but more often they appear in clusters, multiple sprites flashing across the sky above a storm in quick succession. Sometimes a dozen or more in a single second following a powerful lightning discharge. Sprites last only a few milliseconds, typically 3 to 10 milliseconds from initiation to fade out, though the exact duration varies. Despite being so brief, they're surprisingly bright, easily visible to the naked eye if you're watching from the right position. Pilots flying at high altitudes have reported seeing them, and ground observers who know where and when to look have photographed thousands of sprites. The International Space Station, orbiting above the weather, frequently captures sprites from above, providing a unique perspective on these phenomena. The electromagnetic pulse from the lightning strike doesn't just trigger sprites. About 1 millisecond before a sprite appears, to raise often a sprite halo, a pancake-shaped diffuse glow centered around 70 kilometers altitude, perhaps 50 kilometers across and 10 kilometers thick. The halo represents a weaker ionization, not quite strong enough to develop into the full streamer formation that creates the sprite proper, but visible briefly as a faint precursor. Sprite halos can be mistaken for another phenomenon called ELVES, which we'll discuss in a moment, but they're distinct in their timing and formation mechanism. Sprites are cold plasma phenomena, not hot like the lightning channels below. The air at sprite altitudes is so thin that heating is minimal. The glow comes from the excitation of gas molecules, from electrons gaining energy and then releasing it as light, but without the intense thermal processes that characterize tropospheric lightning. This means sprites are more akin to neon signs or fluorescent lights than to lightning bolts, different states of matter responding to electrical energy in different ways. Beyond sprites, there are blue jets, a phenomenon discovered by accident during sprite observations in 1994. Blue jets are narrow cones of blue light that shoot upward from the tops of thunderstorm clouds, typically reaching altitudes around 40 to 50 kilometers. Unlike sprites, blue jets are not triggered by lightning strikes. Instead, they appear to initiate from within the cloud top, from the upper positive charge region, perhaps representing a discharge between that region and a negative screening layer just above the cloud. Blue jets are blue, as the name suggests, because they occur at lower altitudes than sprites. In denser air, where blue light from nitrogen emissions dominates over red, they propagate upward at speeds around 100,000 kilometers per second econd, roughly 1/3 the speed of light, taking a few hundred milliseconds to reach their maximum extent. They're dimmer than sprites, harder to photograph, and occur less frequently, making them less well-studied. But they're fascinating in their own right, representing yet another way that thunderstorm electricity can manifest. A variant of blue jets are blue starters, which are similar but don't propagate as far, typically reaching only 20 to 25 kilometers altitude before terminating. Blue starters might be failed blue jets, attempts at upward discharge that don't quite have the energy or the field strength to push all the way to the heights that full blue jets achieve. Then there are gigantic jets, perhaps the most spectacular of all these phenomena, though also among the rarest. Gigantic jets are massive electrical discharges that connect the thunderstorm directly to the ionosphere, bridging the gap from roughly 15 kilometers altitude, where clouds exist, up to 90 kilometers altitude, where the ionosphere begins. They appear to start as intra-cloud discharges, but then escape the cloud and propagate upward, traveling much farther than ordinary blue jets. Gigantic jets were first documented in 2001, photographed above storms in the Caribbean, and since then have been observed only occasionally, perhaps a few dozen well-documented cases worldwide. They're visually stunning, bright channels extending vertically across vast stretches of atmosphere, often changing color from blue at the bottom to red at the top as they pass through different pressure regimes. They can carry substantial electrical charge, transferring tens of coulombs between the cloud and ionosphere, effectively short-circuiting the normal path of charge flow through the atmosphere. ELVES, an acronym standing for emissions of light and very low-frequency perturbations due to electromagnetic pulse sources, represent something different again. ELVES are expanding rings of light in the ionosphere, typically at altitudes around 100 kilometers, spreading outward in a rapidly expanding circle that can reach 400 kilometers in diameter. They're caused by the electromagnetic pulse from powerful lightning strikes, particularly cloud-to-ground strikes. The pulse travels upward at the speed of light, and when it reaches the ionosphere, it energizes electrons there, which then excite nitrogen molecules, causing them to emit light. ELVES happen incredibly fast, typically lasting only about 1 millisecond, far too brief for the human eye to perceive as anything more than a general flash. They require high-speed cameras to capture and study. The first ELVES was identified in space shuttle video in 1990, though at the time the observers didn't know what they were seeing. The name came later, and the acronym was carefully constructed to fit the mythological theme established by Sprites. There are yet more phenomena, some rare, some poorly understood, some recently discovered. TROLLS, an acronym for transient red optical luminous lineaments, are red spots or streaks that appear after particularly strong sprites, descending downward from the sprite structure. They seem to be a secondary effect, perhaps plasma left behind by the sprite, continuing to emit light as it disperses or falls. Pixies are tiny, brief flashes, pinpoints of light that appear randomly above thunderstorms. They seem to occur independently of specific lightning strikes, though obviously they require active storms. They are so small and brief that they're difficult to study. Visible primarily on high-sensitivity cameras, looking at storms from long distances or high altitudes. Gnomes are another small, brief phenomenon, similar to pixies but perhaps slightly larger or longer lasting. The distinction between gnomes and pixies is not entirely clear, and they might represent a spectrum of similar events rather than truly distinct phenomena. The names, all drawn from mythology and folklore, reflect both scientific whimsy and the sense that these phenomena seem otherworldly, magical even, when first observed. Sprites, elves, trolls, pixies, gnomes, blue jets, gigantic jets. Each name tells you something about the phenomenon while maintaining a consistent theme. It's unusual in science to have such a playful naming scheme, but in this case it works, capturing the ethereal nature of events that flash briefly above storms in the thin air at the edge of space. These transient luminous events, collectively called telos, occur frequently, far more often than scientists initially suspected. Global satellite observations suggest several million TLE events worldwide each year, which means thousands happen every day, mostly unseen because they occur over oceans, remote areas, or during daylight when they're invisible against the bright sky. From the International Space Station, astronauts can photograph TLEs routinely, and ground-based observation networks have cataloged tens of thousands of events. What do TLEs tell us about Earth's atmosphere? They reveal that electrical processes in thunderstorms have far-reaching effects. Literally, the energy in storms doesn't just dissipate locally through lightning and rain, it propagates upward, affecting the chemistry and dynamics of the mesosphere and ionosphere, regions that we usually think of as separate from weather. The electromagnetic pulses from lightning, the upward propagation of electric fields, the transfer of charge between different atmospheric layers, all these connect the TOHsphere, where we live with the upper atmosphere and space environment. TLEs might play a role in atmospheric chemistry, creating reactive molecules in the upper atmosphere, affecting the balance of gases there. They might influence how radio waves propagate, creating temporary disturbances in the ionosphere that affect communication systems. Some researchers even speculate they could have subtle effects on climate, though this remains highly uncertain. What's clear is that TLEs are not just pretty lights. They're signatures of significant energy transfer, of electrical processes, coupling different parts of the atmosphere in ways we're only beginning to understand. Other planets have lightning too, and likely have their own versions of TLEs. Jupiter's storms, vastly larger than Earth's, generate extremely powerful lightning visible from space. Saturn has lightning, detected by spacecraft visiting the ringed planet. Venus possibly has lightning. Even Uranus and Neptune, the ice giants at the outer edge of the solar system, might experience lightning in their thick atmospheres. Where Therese lightning, there might be sprites and jets and ELVES, upper atmospheric phenomena that could be common throughout the solar system, wherever conditions allow electrical storms. The discovery of TLEs reminds us how much remains unknown, how even familiar phenomena like thunderstorms can surprise us with hidden aspects. For centuries, humanity watched lightning, developed theories about it, learned to protect against it, yet never suspected that above the visible storm, invisible to casual observation, these spectacular discharges were painting the upper atmosphere with brief, colorful light shows. It took sensitive cameras and the right observations at the right time to reveal them. And even now, decades after their discovery, TLEs continue to yield new surprises, new types, new questions. Let's return to ground level now, to the practical side of lightning, to how humanity interacts with this phenomenon, and how science and technology have made it possible to understand, predict, and protect against lightning hazards. Lightning has always been both awesome and dangerous, a force that could destroy property, start fires, kill people and animals. Understanding where and when lightning will strike, detecting it as it happens, has become crucial for safety and for many industries. The Earth experiences an estimated 16 million thunderstorms every year, distributed unevenly across the globe. At any given moment, More than 2,000 thunderstorms are active somewhere on the planet. These storms collectively produce roughly 100 lightning flashes every second, more than 8 million flashes per Dalton Y worldwide. Some regions experience far more lightning than others. Tropical areas near the equator, where warm, moist air and strong convection are common, see the most lightning. Central Africa, particularly the Congo Basin, experiences extraordinarily high lightning rates. In the Americas, the Amazon Basin and parts of Central America have intense lightning activity. Southern Asia, especially during monsoon seasons, lights up with frequent storms. In the United States, Florida leads in lightning frequency, particularly the central and western parts of the state, where sea breezes from both coasts collide, triggering daily afternoon thunderstorms during summer months. Other lightning-prone regions include the Gulf Coast, the southern Great Plains, and the Rocky Mountain foothills. These patterns reflect the meteorological conditions that favor thunderstorm development. Warm temperatures, high humidity, atmospheric instability, triggers like topography or converging winds. Lightning poses real danger. Globally, lightning is estimated to cause around 24,000 deaths each year, though this number is uncertain because many lightning fatalities in developing countries go unreported. In the United States, where reporting is comprehensive and safety awareness is high, lightning causes between 20 and 50 deaths annually, with the number showing a long-term declining trend. A century ago, lightning was the leading weather-related killer in the U.S., claiming hundreds of lives each year. Modern forecasting, better shelter, increased awareness of danger. All these have reduced mortality significantly. About 80% of lightning victims are male, a statistic that reflects behavioral patterns more than physiology. Men are more likely to be outdoors during storms, more likely to be engaged in activities like fishing, golfing, or working outside, less likely to seek shelter when they hear thunder. The peak ages for lightning fatalities are between 20 and 60, the working and recreating years when people are most active outdoors. The activities associated with lightning deaths are revealing. Water-related activities, fishing, boating, and beach-going account for a significant portion of fatalities. Fishing alone is responsible for about 8 to 10% of all lightning deaths. Fishermen are often in open boats or standing in open water, prominent targets for lightning, and the noise of waves or motors might mask the sound of thunder that would warn them to seek safety. Beach goers face similar risks, exposed on open sand with surf noise, potentially covering the acoustic warning of approaching storms. Sports activities, particularly soccer and golf, contribute notably to lightning casualty statistics. Soccer fields are large, open, often the highest point in a park, and games can continue even as storms build. Players and coaches sometimes reluctant to interrupt play until danger is obvious. By then, it may be too late. Golf courses are similarly hazardous. Expansive open areas where golfers might be the tallest objects, sometimes tempted to finish just one more hole before heading in. The 30-30 rule offers practical guidance for lightning safety. If you see lightning and count less than 30 seconds before hearing thunder, the storm is less than 6 miles away, and you're in danger. Seek substantial shelter immediately, either a building with plumbing and wiring that can route lightning current, safely to ground, or a fully enclosed metal vehicle. Once you're safe, wait 30 minutes after the last thunder before resuming outdoor activities. Lightning can strike from the edges of storms, from that distant anvil region, even when rain has stopped or hasn't yet begun. That 30-minute wait ensures the electrical threat has truly passed. Detecting lightning, tracking it in real time, has become a sophisticated global enterprise. Multiple networks of sensors monitor lightning worldwide. Using different technologies and approaches, the basic principle involves detecting the electromagnetic signals that lightning produces. Every lightning flash emits a pulse of radio waves, energy that propagates outward at the speed of light. Sensors tuned to specific frequency ranges can detect these pulses from hundreds or even thousands of kilometers away. The most advanced systems use a technique called time of arrival, combining data from multiple sensors. When a lightning flash occurs, the electromagnetic pulse reaches different sensors at slightly different times, depending on their distances from the strike. By precisely measuring these arrival times, accurate to billionths of a second, and knowing the locations of the sensors, computer systems can calculate where the lightning occurred through triangulation. 3 sensors can give a rough location. 4 or more provide precise positioning, often accurate to within a few hundred meters. Some systems also measure the magnetic field direction of the pulse, providing additional information about the strike location. Combining time of arrival with magnetic direction finding gives the best accuracy with the fewest sensors. VISA-LAS Global Lightning Detection Network, called GLD360, uses this combined approach with sensors distributed worldwide, achieving location accuracy around 1 kilometer globally and even better in well-instrumented regions. These networks can distinguish between cloud to ground and intra-cloud lightning based on the characteristics of the electromagnetic pulse. Cloud to ground strikes produce distinctive signatures, typically stronger and with different frequency content than intra-cloud flashes. The networks classify flashes, estimate their peak current, track individual storms, even identify positive versus negative strikes based on the polarity of the initial pulse. Earth Networks operates another major detection system, the Total Lightning Network, which emphasizes detecting intra-cloud lightning, since intra-cloud flashes precede cloud. To ground strikes in developing storms, tracking intra-cloud activity provides earlier warning of severe weather. Earth Networks has deployed over 1,200 sensors globally, creating dense coverage in many regions, allowing detection of relatively weak lightning that other networks might miss. The Worldwide Lightning Location Network, WWLN, takes a different approach. Operating from the University of Washington, WLN uses very low-frequency radio signals to detect lightning globally with a network of more than 70 sensors. WLN doesn't catch every lightning flash. It's most sensitive to powerful strokes and has lower detection efficiency than commercial networks. But its global coverage and free availability for research purposes make it valuable for studying lightning climatology. Long planetary scale phenomena. All these networks feed data to weather services, aviation authorities, emergency managers, utilities, anyone needing real-time lightning information. The National Weather Service uses lightning data to improve severe weather warnings, to identify storms that are strengthening, to track thunderstorm motion. Airlines use it to route flights safely. Avoiding areas of active lightning. Power companies monitor lightning strikes to their transmission lines, dispatch crews to damaged locations, predict where outages might occur. Wind farms, particularly concerned about lightning damage to turbine blades, use detection systems to assess risk and optimize maintenance. The data reveal patterns, help refine forecasts, contribute to climate studies. By analyzing millions of lightning flashes over years, researchers map lightning climatology, understand how lightning frequency relates to temperature, precipitation, atmospheric circulation patterns. Some studies suggest lightning frequency might increase as global climate warms, since warmer air can hold more moisture, and warmer temperatures enhance atmospheric instability. Tracking long-term changes in lightning activity could thus serve as an indicator of climate change. One more way that understanding this phenomenon contributes to broader scientific knowledge. Benjamin Franklin's famous kite experiment in 1752, risky as it was, established that lightning is electrical. Franklin's subsequent invention of the lightning rod provided the first effective protection. A simple metal rod extending above a structure, connected by a conductor to the ground, offering lightning an easy path to Earth that bypasses the building. The principle remains valid today, though modern lightning protection systems are more sophisticated, using multiple rods or air terminals, down conductors with specific routing, grounding systems designed to dissipate charge safely into the earth. Tall structures, skyscrapers, communications towers receive hundreds of lightning strikes per year. The Empire State Building in New York reportedly gets struck about 25 times annually. These structures incorporate extensive lightning protection, designed so that strikes, though they carry enormous current, cause no damage. The metal framework of the building itself often serves as part of the system, the lightning current flowing through the steel structure to ground. Aircraft encounter lightning regularly. Commercial planes are struck on average once or twice per year. The aircraft's metal skin serves as a Faraday cage, conducting the current around the passengers inside, then off through static discharge wicks on the wings and tail. Modern aircraft are designed and tested to handle lightning strikes safely, though pilots still prefer to avoid thunderstorms for other reasons. Turbulence, hail, the general violence of severe weather. Despite all this technology, all this understanding, lightning retains its power to awe. A close lightning strike remains visceral, immediate, an experience that reminds us that we share our planet with forces vastly exceeding human scale. The sight of lightning illuminating the night, the sound of thunder rolling across the landscape. These speak to something deep, some ancient response to power and beauty combined. Lightning appears in human culture everywhere. In mythology as the weapon of gods, Zeus and Thor wielding thunderbolts. In art as a symbol of sudden change or divine presence. In literature as a metaphor for revelation or destruction. We use lightning symbolically. Lightning, fast for speed. Lightning bolt for sudden realization. Bolt from the blue for unexpected events. The imagery is universal, transcending cultures because lightning itself is universal, experienced by every civilization under natural skies. And there remains mystery, questions still unanswered. The exact mechanism that initiates the stepped leader isn't fully understood. Why some storms produce more lightning than others of apparently similar structure puzzles researchers. The details of how ball lightning forms. If the silicon theory is correct, or if something else is happening, await more observations, more data. The full effects of TLs on the upper atmosphere, their potential role in atmospheric chemistry or climate, remain active research areas. Each summer storm, each flash illuminating clouds, each boom of thunder carries these questions, these mysteries, along with the elegant physics we've come to understand. Lightning remains an active field of research. Papers published regularly, new observations from improved sensors, new models run on powerful computers, new theories proposed and tested. The phenomenon that has captivated humanity since our ancestors first cowered in caves during storms still yields secrets, still surprises, still inspires. As you drift toward sleep tonight, as your breathing slows and thoughts quiet, you might find comfort in this understanding that the lightning flashing above summer landscapes follows rules, expresses fundamental forces, connects to the same physics that orders all of existence. There's a beauty in that knowledge, a peace in understanding that even the most dramatic natural phenomena arise from principles we can comprehend, study, predict. The universe is knowable, its processes discoverable, and lightning, awesome as it is one more chapter in that endless book of natural law. So rest now, knowing that somewhere, right now, storms are building, charges are separating. Lightning is flashing to ground and through clouds and up toward space, maintaining the global electrical circuit, redistributing charge between sky and earth, performing its weather. Rest knowing that science illuminates these processes, that human curiosity has reached into the storm and brought back understanding, that what once seemed pure chaos has revealed its underlying order. If you've found peace in this exploration, if the gentle unfolding of lightning science has brought you calm, consider liking this video, subscribing to join more tranquil journeys through science and wonder. Share this with someone who finds comfort in knowledge, who sleeps better understanding the world. But for now, simply rest. Let go. Allow sleep to find you easily, naturally, as inevitable as the discharge that completes the circuit between cloud and ground. The storm above, the quiet below, the flash and the darkness, the crack and the silence. And you, resting here, breathing slowly, are part of that same rhythm, that same universe, connected to lightning and stars and everything that flows and changes and endures. Sleep well,